Okay, so I built this lecture by the first two lectures because this is taking everything we learned here and put here. So we learned about GNN, attention, transformers, cell generation. All of it will go into particle flow. This is a work that I did with many people, but from Weizmann and the two people who helped me to prepare this specific lecture were Nilot Palkakati, my student, and my postdoc Etienne Dreyer. But Lucas was also part of it, and other people, as you will see. It's a big project. We worked on it for 3 years or so. So that is what left today. We constructed particles in jets using hypergraph p-flow. So the whole idea started a few years ago when you wrote a paper towards computer vision particle flow. And we want to reconstruct particle in jets. You see the detector output and you want to reconstruct the particle. So in 1964, when they started particle physics more or less, and there was the omega minus discovery in a bubble chamber, they used to do things to reconstruct particles simply with special people who were trained as scanners, that's how they call them. And they use special rulers and tools, geometrical tools, in order to draw tracks. And for example, they drew the tracks that they could see because they could see only charged tracks. The one they couldn't see, they kind of visualized them. And that's how they used their imagination to make the point and get a Nobel Prize. So that's the omega minus discovery. The big change in the field came with Georges Charpak that invented in 1968 the multi-wire proportional chamber, but got the Nobel Prize only in 1992. And this paved the way to the modern experiments. One of the first one was the UA1 at CERN, which discovered the Z boson, and Carlo Rubbia and the accelerator guy, Van der Meer, got the Nobel Prize in 1984. And this led us to there was LEP, Large Electron Positron Colliders. I was working in 2 experiments in Opal and Delphi. But then came what we're doing today. The LHC, the Large Hadron Collider, in the same tunnel that we used to run the Large Electron Positron Collider, same tunnel, 27 kilometers tunnel. And there we have Atlas and the CMS. There are other two, but Atlas and CMS are aimed at these things that we are talking about today, not the LHCb also in a way. And there's another one, Alice, that is doing heavy ions, things like that. And there was one discovery in this experiment, which was the Higgs boson in 2012, which gave the Nobel Prize to François Englert and Peter Higgs in 2013. So what is a modern detector? A modern detector is like an onion. It's made of layers. So there is the tracking layer, then there is the electromagnetic calorimeter, which stops the electromagnetic interacting particles like photons and absorb their energy. And we can try to measure how much was absorbed and guess the particle's energy. And particles like protons and neutrons will continue here and shower whatever they have to shower in the hadron collimator, made of usually of iron and things like that, where they stop it. And the only particles that won't stop and go out are the muons. Of course, you won't see neutrinos here. So Let me show you how it really looks like. Here is how a photon looks like with a real detector simulation. The photon will go here, we leave nothing in the tracking chamber, of course, and will deposit all of its energy in the electromagnetic colorimeter. An electron will be similar. It's very hard to tell an electron from a photon, except that the electron will leave a charge tracker, and that's the way that we can tell this is an electron. But you already see the problem. The electron will have a track which will bend according to its energy, but will also deposit energy here. So if we count the energy here and here, we do double counting. And it gets more problematic. Because here you have a neutron. You see that the neutron is not charged, but it also deposits some energy in the colorimeter here, and most of energy in the hadronic colorimeter. And if you don't do the right calculation, you will do double counting. Same thing if we go to, for example, a proton, it will be like a neutron. They're very similar, as you know, except from the charge. So it will leave some energy in the electromagnetic and deposit most of energy in the hadronic colorimeter. This is a K long 0. Same story, you see the pattern of neutral hadronic particles, you see the pattern. So how would you tell a K long from a neutron? Very difficult. So you have to look at the shower shape. And what can look at the shower shape? The machine learning, right? So you see all these particles, all of these are 50 GeV particles, all of them. And you see here the photon, the electron, the K long, the pi plus, for example, the neutron. Now what happens if all of them comes in a jet which overlaps each other? What do you do then? How do you know which is which here? How do you tell which charged particles are here? And especially, how do you tell which are the neutral particles here? This is the dream of the physicist. The dream of the physicist is to look at these things and the traces in a detector and tell you what is going on there. And more than that, it's even more complicated because low energetic hadrons will not get to the hadronic polymeter. They will exhaust their energy already in the electromagnetic colorimeter. In a nutshell, what we have here is we have the physics input, the Feynman diagram, which will then give, if it gives jets, they will shower, hadronize and all this stuff, and they will produce the final particles. These did not even go to the detector yet. Now they go into the detector. The detector will issue electronic signals, which we then want to read and somehow interpret. So, this is a hard process, but this is not all that is going here. We will start to have some parton showers there, if we have quarks, etc., and they will complicate our life. At the end of the showering, when we are exhausted out of the energy of the showering, we'll get the hadronization. And then the charged particle will leave the traces in the detector. The pi zeros might decide to decay to mostly photon-photon. And now we will have to tell if these are two isolated photons or these two photons come from pi zero. This is a challenge as well. We are already in the detector regime here. And then we go to the hadronic shower here, and we have to tell shower from shower and overlapping showers. And this is not the end of the story. because we also have underlying events. We have the two spectator quarks that interact as well. And we have the pileup, if you know what it is. This is a complicated story. But at the end of the day, what we get is the data from the detector. And this is what we want to analyze. So analyzing it is doing the inverse problem. We look at our tracking, we look at our clustering of all the cells deposit energy, and we go backward. From this, we want to reconstruct by regression, if you like, the momentum of the particles, to isolate the particle, and then even classify them, to say this is a photon, these are E mu tau, this is hadrons, and which hadrons if we could, and also try to guess what are the neutrinos. For that we need an hermetic detector. And I think that the final goal will be to tell what was the process that gave us this data. And since these 2, 3, or 4 processes can give the same final particles, can we give some probabilities to which one is the one that we are looking at? So I would say that the holy grail of the particle physics is to go from the detector output into the processes that initiated the particles. This is the holy grail. We are not even close to that. In the language that I showed you before, this is the holy grail. So where can we hope to do something? We can hope to do something which is partial. We can hope to look at the detector output and predict which truth particles hit the detector, knocked on the door of the detector. The next stage will be one that they can factorize. You can then do that's something else that we work on. It will be like something like set. If this is a set of particles, in the language of deep learning, it will be set to 3. Because we want to know now all the decay chains, including fragmentation and all this, and know where it came from. But let's first tackle the most difficult problem. How do we construct from the detector signals the final particles that knocked on the door of the detector? So particle flow is combining track and calorimeter information in some complementary way while avoiding double counting and tell which particles are happening there. So I already said there is double counting of tracks and energy deposits. The traditional way before the machine learning era, and most experiments, if not all, are still using it. And I will tell you about Atlas because that's what I was working on, still working. The first thing you do is you have lots of cells. So to make your life a little bit easier, you cluster the cells which are adjacent and which have high energy significance around some seeds into something we call topocluster. These are not particles usually, but we build particles from the topocluster. We don't lose anything, we just cluster the cells. Then we find the associated tracks. Then we look where the track points. We try to associate the tracks with the clusters in the calorimeters. We try to guess how much energy the track deposits in the calorimeter, subtract it from the readout of the calorimeter. What you're left with are neutral particles. It's very hard to really tell particles from it, but you can try and calculate the correct total energy of the event this way. Very hard to tell particle from particle, but you can try and guess how much energy, the charge track deposited in the calorimeters, subtract it, and get the total energy of the event. So the question we ask ourselves is, can we approach this problem as a machine learning task? Yeah.
So in part one, how exactly do you get the boundaries of these total clusters?
This is, you have the reference here. This is a kind of a clustering algorithm. Let's find seeds. Let's start to collect things around the seeds, see if the seeds has to be changed. It's an iterative process. You have the reference down there. But it's something that works well. Only Atlas are doing it. I think CMS are working directly with the cells. I don't know. Anybody from CMS here? Yeah, I think you work directly with the cells. You don't bother to do the topo clusters.
Yeah, usually we take we reconstruct the particles and then we cluster it.
Yeah, you first do the reconstruction, then cluster.
Yeah.
Okay, what's the work plan? In order to learn, you need a detailed, realistic detector simulation. Because neither Atlas nor CMS will allow you to really use their data in order to develop your private things. So if you want to develop something without having to have the approval of the collaboration, and especially if you're a phenomenologist and you want to do things that experiments are doing and you can't get access to the experiment, but even the experimentalists, they want to develop things without being tied to the experiment, and which might take years after years and nothing happens. So we decided we have to develop our own realistic detector simulation that can be adjusted to look like Atlas or CMS. There is one like this. How is it called? That everybody's using? It's called Delphis. But Delphis is not detailed enough. We wanted really the cells, so we can build everything from the cell level, not just smearing, okay? So we built our own detector, which I'll introduce to you today, and everybody can use it. The second is proof of concept. Can you tell a neutral hadron, like pi 0 goes to gamma gamma, from an overlapping charge hadron when they overlap each other? And the third thing was the real thing, can you reconstruct a whole jet? So that's the talk. Let's start with the first item. This is a detector that we built for a few years. It's called COCOA, Configurable Calorimeter Simulation for Artificial Intelligence Tasks. And it's available since a few months now. It's made of inner tracking system with a 3.8 Tesla magnetic field, with a solenoid, with 9 layers of thin silicon iron interface. This is surrounded by electromagnetic calorimeter with 3 layers, which have a lead argon mix as done in Atlas. This is surrounded by the hadronic calorimeter with another 3 layers. And this is COCOA. So the overall description of COCOA is 3 electromagnetic layers plus 3 hadron layers, concentric. It's interface to PITIA, to the event generator. This is made by GN4, and it exists in an environment of a magnetic field, just like a real detector. This is the paper. As usual, you know Lucas, who is here, and you heard about my student and my postdoc. And as you can see, it's a project of many, many people that worked many years on this. So what you're going to see now is a simulation of a collision with COCOA. So you see, it's very detailed. It's not made of smearings. And if you want to do tasks that involve really going to the real level of cells, this is the way to do it. There's no other way. That's why we had to do it. Proof of concept. So as I said, you can go to the reference here and there is a description of the detector. There are cards, you can operate it, you can run it, you can ask questions if you have, we will help you, we will make you run the detector, and you can do whatever you like if you like to do. Anything. It's a better substitute to Delphus in that sense. Much more detailed and realistic. So the second question we ask is, can you tell a neutral hadron from an overlapping charge hadron? This is another paper. This is sort of an older paper, so only me you know from this paper. And it was the cover article of EPJC because it's first of its kind. First time somebody tried to tackle particle flow with, at that level with machine learning. What is this figure that you see here? I will tell you in a second. So in this paper, we shot overlapping pi plus and pi 0 that went into gamma gamma, and we tried to build a convolutional network-based machine learning algorithms to tell the pi 0 from the pi plus. And of course, we compared it with the parameterized p-flow, which is exactly what I told you, the good old way in which you parameterize how much energy is deposited by a charged particle in the calorimeters, and you subtract it. So this is what everybody is doing. So here is an example of what happens in the truth equal, the layers 1, 2, 3, and the first hadronic layer. What happens when you have a truth neutral deposit, and the prediction of the network, and the prediction of the classical parameterized p-flow algorithms. It's enough to see that if I go here, the machine learning algorithms can tell that there's no deposit from the particles in the third layer of the ECAL and the fourth layer, in the first layer of the HCAL, but the parameterized p-flow cannot tell it. And the parameterized p-flow is doing is not doing a good job, while we managed to really tell the neutral from the charge. So that brought us the idea that maybe we can go a little bit further. I don't even know what is Topaz AI. It's one of the most successful image processing programs in the market. It competes with Photoshop on AI stuff, and this is the way they do, for example, sharpening. You have an image and they sharpen it. So the question was, can we sharpen a detector? What does it mean? It means in life we don't have money to build a very expensive detector with very fine cells. We don't have the money to do it. It costs a lot of money. But in simulation, we can do it easily. So maybe we can train a network to match low resolution to high resolution detector readout. We shot a pi 0 that goes to 2 photons. In our real detector, they look like they merge. But there are patterns in the way that they are shape of the shower in the cells. Maybe these patterns can be revealed by a higher resolution detector that we build with simulation. The network knows how it will look like because we trained it. And then it can tell, you go back, you infer backward, and it can tell that there are 2 photons there. For example, here you see how a low resolution detector looks like and how a super resolution detector will look like. This you cannot build in reality. You don't have the money and the resources. But this you have. That's what you work with. So here's what we do. Here are the two photons. They deposit their energy in the calorimeter, but you cannot tell between one and another. But the simulation can tell that these are two photons. And when you infer back, you say that these are two photons with this and this energy. So that was something that we do as a bonus to our thing. I hope you understood the principle. Okay, let's go to the real meat. Can we reconstruct a whole jet? Can we reconstruct this jet? So this is the paper. Again, Lucas is part of this paper. He's here. And there are many people here. I will give my talk in this way. I will start with a problem, we'll describe the data set, and then I will go to the deep learning model. I will describe well two of the three methods here, and I will show you how well we are doing. Let's start with the problem. You already know it. So the problem is, as we said, to go from the detector into the real particles, the true particles that hit the door of the detector. So we have the final states. We have a set. The target is a set of the truth particles. That's the target. We know it because we train it with simulation. So we know that's a target. This will go to interactions in the detector. And we try to reconstruct it, to predict these particles. We try to predict it. Then we can do analysis. So what we have is a real problem of set to set. We have the set of cells and tracks, or topoclusters and tracks, doesn't matter. Depends which detector you work with, how you work, from which you want to infer the set of truth particles that hit the detector. In other words, infer the set of particles, reconstructed output, which produce the set of energy deposits in the detectors. Sets of cells and tracks. Is the problem clear? So I think that with the background that you have now, you really feel it's a set-to-set problem that there is a chance to solve, because you have tools now. Of course, there are lots of challenges here, like the physical overlap, the pileup, and the data is very, very complex. There are 3D spatial correlations, lots of layers of detector, lots of cells, and they talk to each other, and some are close by, some are far away from each other. It's very similar to the classical problem of identify a dog or a cat from a picture. Is it a dog or a cat? So, and if the picture has more than a dog and a cat, you want to classify and say here is a, you want to segment the picture, suddenly say this is a dog and this is a cat, or autonomous driving. So it's very similar. We have a detector. We have all the hits of the cells that you can treat them, if you like, as point clouds or whatever. And you want to first identify the number of objects and then classify them. We already saw it twice, right? Identify the number of objects and classify them. So it's a set-to-set task. The input set is clear. The output set is first reconstruct the particles, find the cardinality, which is also something we did already. And once you have the cardinality, now you have the tool in which you can try and classify them. In our case, we did a very simple classification. neutral hadrons, charged hadrons, and photons. You don't see here electrons and muons because of two reasons. First of all, there are special algorithms to identify electrons and muons, and they work very well, and we know how to do it. But the second thing is that in jets, you won't find a lot of electrons and muons, less than 5%. It's not many electrons and so if you want to train it, you need much more data. But it's not really the problem. The problem is to identify the charged hadrons and tell them from the other, and tell when they overlap how much energy they carry and what is left for the neutral. That's the real challenge here. And in the end, you want to regress the location of the bounding boxes in that sense, regress the properties of the classified object, which is the direction, eta phi, and the momentum, the pt. That's the story we're trying to sort out and solve. What would be the data set that we worked with? We used the single light jets. We train with 50,000 and test with 30,000. This was done with transformers and diffusion. This is the mid-journey, okay? So now you want to dive into the deep learning. That's what I type in mid-journey, dive into deep learning, and that's what it gave me. So the deep learning model. So now there'll be a 5 minutes repetition of things that we talked about already, which is the Y graph. Because the first paper that we did with CNN. But you see, even with the CNN, most of the information, empty cells, nothing. It's so sparse that you don't use it. It's a waste of resources, memory, and everything. Graphs capture spatial correlations and codel in irregular detector geometry, because our real detector is irregular. We don't have just some piece of material that we shoot forward. We have layers, and they talk to each other. We have edges. We have corners. It's a very complicated detector, and a very special spatial relationship. And there is variable cardinality, because we always start different number of cells, different numbers of track, and then different number of particles. We have to predict the cardinality. So the cells and tracks are the nodes. And you'll see how we use the edges. The edges either tell us if they are connected or not, or even some more sophisticated stuff, as we will see. When we start with, we see another possible problem, which is that the features of the cell are different than the features of the tracks, not only in content, but also in the number, okay? Which we have to solve. So this has to do with the spatial features, and this has to do with the kinematics. So we have sparsity, we have a set-to-set problem, and obviously, if you change the location of the cells and the tracks with all the properties, you drag them with you, it shouldn't affect the output, so it should be what we call equivariant.
Why to use both X, Y, Z and angular?
It could be that I made a mistake when I typed. What did I see?
So like X,
Yeah, no, you're right, I don't need that. You're right, it was my typo. Okay, you see that I already said it, but this is a real picture of an event, which I will use a few times in different aspects. The x-axis shows you the truth particles. Okay, true photons, true neutral hadrons, and the charged hadron is the dark red or whatever, and the yellow kind of is the photons. That's when you enter the detector. Then you have the 3 colorimetric layers and the 3 hadronic layers. In these specific events, you see how complicated this is. All one graph. This is all one graph. And you see how complicated, because one feature would be the layer, okay? One feature would simply be the layer. And you see how complicated, when they talk to each other, how complicated it is to talk, because it talks to its adjacent nodes, but also you should take into account the nodes from the next layer, because they're correlated. So correlated inside the jet are coming from spatial relationship here. So the first thing you want to do is translate everything to the language of the detector, what we call embedding. So this is done with the, okay, that I already told you. This is how graph works. You know already how graph works. There is message passing here where you take information from the circle of friends that are close to you, every loop that you do, and you repeat it a few times. Remember that? Remember that? It's okay? Okay. So we have a data graph in the input. In the output, we want to predict the particles. That's what we want to do. So the node encoding is something you're familiar with in another context, but it's very similar to what we saw. So we have the cells here, or the topo cluster, doesn't matter. They have their features. Their number and content might be different than that of the tracks. That is why I take, but they have a fixed number of features. So I can use an MLP. So I embed everything in vectors dimension 100. That's the beginning of my embedding. I concatenate the tracks and the cells. I send everything to the GNN mixer. I run it 4 times. I get the computer language objects here. I know where they came from. So I can tell, if I want, which of the cells, which of the same cells came from the same topo cluster. So I can, for example, these two, the first two belong to the same topo cluster, so I can combine them. And then, so I have now the representation of the topo cluster. If I want to work with topo clusters, not a must. But we wanted to save time and all this. We could work with cells, but it took too much time. It was too much memory consuming, etc. In most of our examples, in the examples I give today, yeah. And then we had these ones were either topo clusters or tracks which were not connected to topo clusters. So this is, here we have topo clusters and the charge tracks and the single topo clusters that's a topo cluster that did not connect to tracks. It will also be here. So this is what we have here. So I have a representation, embedded representation of topo clusters and tracks. That's my input. Embedded representation of topo clusters and tracks. Sometimes I'll say cells and tracks, same thing from this point of view. But I have an embedded representation. That's my beginning. And then I can start to build my deep learning architecture here. So we use 3 deep learning architectures. I will only talk of 2. Once was invented by a guy from CMS, Jan, object condensation. Once is very similar to something I showed you yesterday, the slot attention. Because the slot attention is great here, right? We want the particles to be slots, and they will accommodate the topo clusters and tracks. Which topo cluster and tracks belong to which particle, right? That's exactly what I want. I have particles and I have the topo cluster and tracks. and I want to decide. It's exactly what I want. So slot attention will come here, and the hypergraph is something that we use here for the first time in high energy physics. So in the object condensation, which I will not talk about, the idea is that one node is the dominant, and it describes the particle, sort of, and you collect all nodes around it, and there's one representative node. But I'm not going to talk about it. So here we use cells and tracks, not topoclusters. The other two I will talk about. The nodes are topoclusters. The topocluster can deliver energy to more than one particle, because two particles can deposit energy, and they will be assembled together as one topocluster, and that is related to the question that I was asking. You don't lose anything, okay, by doing this, but it will make your life harder, because you will still have the task of telling what is going on, right? You just deal with bigger objects, but the object can share particles. So we'll talk about the slot attention one. This uses the learnable attention in latent space, like we saw yesterday. And I will introduce the hypergraph particle flow, which is based on the physics, what is called physics inductive bias. So let's start with something we already know about, the slot attention. That will be easy because we saw it yesterday. So first we have the embedding. That's exactly what I show you. I start with the cell features. Same thing I showed, tracks. I do the embedding, the mixer, and then I collect the topoclusters, and I get the embedded presentation of the topoclusters and tracks going into my deep learning architecture. So that's already said, that the mixer here is like is the update of the nodes by 4 successive blocks of message passing along the edges, as I said already. And the topocluster representation are computed by the energy weighted mean of the cell representation vector belonging to the topocluster. So we don't just add the cells that belong to topocluster, but we add them weighted by their energy. But that's just a detail. And now we go into the slot attention, and that will be very familiar to you. Okay? Because the first thing we do, we take the node representation, the embedded one, we pull it or aggregate it or whatever, we find a global presentation on which we operate an MLP on the features, and we use a classification problem with cross entropy loss to predict the cardinality. Okay? Then we take this node representation and we feed it into an attention mechanism here. The slots will be the particle flow objects. We take the embedded particle flow objects to an MLP, and this will be our input, which we concatenate with the global representation. We saw it yesterday, exactly this. Then we do the slot attention here. After which we get we do it 3 times. After 3 times, we get the Z. Remember the Z of yesterday? The outside of the key queries, you get the output of this. The updated representation of the slots, right? Remember? Yeah?
Yes.
Okay. So here we have now our final output from the slot attention, which means that these are the particle flow objects that were paid attention by the cells and tracks with the right amount. It learns it, and it gives us the object on which we operate two MLP. One MLP will regress the properties of the object, the kinematics, PT, eta, phi, with an MSC regression loss. The other MLP would use cross entropy loss to predict the classes of the particles that come here. Charge hadron, neutral hadron, or photon. Is that clear? There's nothing special above yesterday. That's exactly what we saw yesterday.
Not entirely clear. So particle flow objects are queries here.
Particle flow object will issue the queries, yeah.
And from this node representation would be keys
Keys and values,
and values.
yes.
And this cardinality is to determine the number of particles or
The number of objects, of particle flow objects, of particles, same thing. But when you train, you know the number of particles, so you will use the trained number. Only in real data, when you don't have a choice, you will use what the prediction gives you.
So where does the topo clusters come into that?
The topo clusters are here. Tracks and topo cluster come here. These are the things that the tracks and topo clusters go into the particle. For example, if a particle is a charged particle, the track cannot, there will be simply a 1 here, because a track can simply give you a particle flow object. You cannot have a track which is divided by 2. The track points only to 1. But when it's a topo cluster, it can divide itself into 2. Okay? Yes?
Do you generally train this all at once or all 3 tasks individually?
This is trained separate. The cardinality is trained separate, and the rest is trained together. To be more specific, we train charge and neutral a little bit different, but I don't want to go into these details. That's in the paper, okay? Okay, now the main thing I wanted to talk about, which is new to you, I want to introduce it to you, is hypergraphs. Nobody talked about hypergraphs, right? Okay. Hypergraph is a generalization of the graph. In a graph, an edge could be connected only between 2 nodes, each edge between 2 nodes. In a hypergraph, I can have hyper edges, where edge can connect, not connect at all, it's maybe 1, but it can connect 2, 3, or 4 nodes, whatever I like. Which means that this kind of edge is updated together, you understand? It's not separate. For example, between here and here, there can be an edge like this, and this node can share an edge like the usual one, but not only with 2. So when we do the update of the edge, it will update the whole of the green, not only this. Understood? Together. That's the whole idea. But it's a game changer. Why? Because there's another way to look at it, and then you'll see. And this way is if I have the nodes here, and the hyper edges I put as objects here. If I do this, something interesting happens. This is a bipartite graph in which you see something that reminds you very much of attention division, okay? Or you can look at it as what we call incidence matrix. the green and the blue, let's see, like this. 1 to 5, nodes 1 to 5 share hyperedge green, right? 1 to 5 share hyperedge green. 1 to 5, okay? Node 1 to 3 share hyperedge blue. 1 to 3 share hyperedge blue. The red one only connects 3 and 4. So if I want to predict an hyperedge, what I want to predict is this incidence matrix. That's the easiest way to look at it. Now there could be different values here. That would be our tracks and topoclusters, and that would be our particles. So this topocluster distributes its energy between the green and the blue particle. This one, green and blue as well. This one, blue and red. This one distributes all of its energy to the red, and this topocluster distributes its energy to the green. The mathematics is very similar to graph. It's a little bit more complex. It has the vertex, the node. It has the edge, the hyperedge, and it has the incidence matrix, which describes all the connections. We think that particle flow, oh my God, why doesn't it, it's not, wow. Give me a second. No, there's only one way. I think the problem is here. I need to restart the computer. How much time I still have? I don't know. Let's see how much I have. You think the problem is in the electric? Oh, I don't believe it.
Missing edge.
No, but it still didn't help. Oh, thank you. No, it's working. For a change, it was not my fault. Okay, why do we use a hypergraph? We think that particle flow is a natural problem of hypergraph. We will show that when you use hypergraph, you have physics interpretability. I will show you now a little bit. I have the truth particle here that I don't know. I know them only when I train. I have the detector readout, the topoclusters and the tracks. And I have the reconstructed particles, which I want to predict by them the truth particle. This is clear, right? So what I have actually, let's have a look. In the input I have this bipartite diagram, which describes the hypergraph. I did not push the hypergraph. It came naturally, you see? Came naturally, because that's what I want to do. I have truth particles, and I have the topoclusters and tracks, and I have the detector output. And what I want to do is to predict the mirror image. If I predict this, I know this. Teaching is like an autoencoder. This should equal to this. That's the teaching. That's what it wants to learn. So I have an input graph from which I have to learn the output graph. So I have an incidence matrix, and I want to predict an incidence matrix like the one that I have in the input. I want to predict it. Now, a big difference between this and what we saw so far is that this is not in the latent space. This is in the real world. I really know it. I know the energies. I know the particles that hit. I know the energies. I know the energies of the topoclusters in the detector when I teach it. So I have a target hypergraph and a predicted hypergraph. So it's a set to set. So step one, encoding. Stem sorry, I don't have to repeat it again. Cell feature, track feature, ta-da, ta-da, ta-da. I get the topoclusters and the tracks. Embedded. Second stage would be to learn the incidence matrix or to learn the hypergraph. Last stage will be to look at the hyper edges, because the hyper edges are my particles, to regress their properties and classify. Is this clear? Okay, let's talk about the incidence matrix. I'll show you the physics behind the incidence matrix now. I have the rows of the tracks and topoclusters and the columns of the particles. Suppose I have a top cluster of 40 GeV that distributes its energy to 3 particles. 30 GeV here, 10 GeV here, and 0 here. So I normalize it, so I have 75% here, 0.25, and 0 here. So that's what I will put in my incidence matrix, the one that I want to learn. 0.75, 0.25, and 0. That's why when I learn, I will softmax there, because it has to be normalized. But that is energy conservation. That's physics. So I have a physics input into my machine learning problem. We call it inductive bias. And we can approximate the particle energy. Particle energy is the sum of the energy here as incidence weighted sum of node energies. We will show later how we do it. So how do we learn the incidence matrix? How do we learn it? That's a very busy slide. Let's try to go. So since I don't know how many particles I have, and since I don't want every time to use a different matrix, I will assume that I have k, say 20, 30 particles, and that's it, maximum. And I will fill the matrix, I will pad the matrix, and I will add another line which will be an indicator. Is there a particle or is there not a particle? 1 or 0. So this is a learnable, this is the cardinality, right? This is a way of looking at the cardinality. It's a cardinality learning, right? And because the sum of the ones here will be what is the cardinality. So I can use binary cross entropy to learn the indicator. So what is going on? Okay, maybe somehow I'm kind of attracted to the board. What is more convenient to you, that I do it like this or that I go to the board?
Probably the pad, because then you don't hide.
Only pad. Okay. You don't tell it to the people who write on the board, huh? Okay, so I'll try to use the pad. Somehow I'm dragged to the board all the time. Okay, what do I have in the incidence matrix? Let's call EIA, line I, column A, topocluster I, particle A or particle B, okay? So EIA will be the amount of energy that particle A, the amount of energy the particle A contributes to the total energy EI of node I. How much energy this particle contributes to this topocluster, or if you like, how much the topocluster contributes to it. Okay? And now I normalize it. I normalize it by the row. Because what do? I take EIA divided by sum of EIB over the particle. So I normalize the row. So that should remind you the 0.75 that you saw here. So in order to learn this, we use the incident loss will be done with the KL divergence between the distribution of the target cells of the topocluster and the predicted ones when I do them softmax, so it's all normalized to 1 as it should be. So I have two kinds of loss, a BCE loss and a KL divergence loss. So this is the way I learn the incidence matrix, I learn it. The mathematics was first introduced with this paper by these three people here. You have the archive here. That's a mathematics paper. And it's funny that we learned it because we wrote another paper that I showed you in the first lecture about how to make vertices out of tracks. So we use graph to do it, remember? How to make vertices out of tracks. We use, do you remember that? The first lecture I showed you,
Slot attention.
not slot attention. The first lecture, I show you how we do set to graph. And I show you how we take tracks and we decide which tracks belong to which vertex. How to build from a jet that has tracks, how many vertices I have there. So we use graph there, and they took our paper, they are mathematicians, and they show that with hypergraph they do a little bit better, a few percent better than us. So they cited us and we saw the paper, and then we said, hey, we can use it for something else. So the way that it works in their paper is a recurrent thing, like we update again and again the graphs. You do first round, you do it 16 times until you build up your final incidence matrix. So now that you have the incidence, the predicted incidence matrix, you can try to deduce what you want from it. So let's talk about interpretability, physics. So I want to regress the PT of the charged particle. For charged particles, you cannot do much better with eta and phi. You can take eta and phi as is. Tracks are very good proxies for charged particles, very good proxies. So what we do is, we first of all separate the inference networks for charge and neutrals. We do them separately. Because for tracks, we just interested in the PT. So what do? We theta learn hyper edges. We add to it, concatenate it with the features of the charged particles, PT, eta, and phi. So now instead of have a dimension 100, we have a dimension 103. We use on MLP with an input of 103 to predict the delta PT. It's sort of the idea of residual, okay? We think we have a good proxies of PT, So let's help it, okay? And give him the proxy for the PT and predict only the delta PT. Once we predict the delta PT, which turned out to be better than predict the whole PT, we add to it a track PT and we get a particle PT. For natural particles, we have to be a little bit more sophisticated because we don't have the track which has we have the track energy and we have the eta and phi of a track, so we have half of the work done, half of the cake baked, okay? Neutral particles is a story, it's always a story. So here's what we do with the neutral particles. We build our proxy for neutral particles using physics considerations. So suppose we learn this part of the hypergraph, and this is 0.7, this is 0.4. So this will be translated into 7 GeV and 8 GeV because we know the energy of the topo cluster. This is a given thing, okay? What the hypergraph tells us is the 0.7 and 0.4. We know about the 10 and the 20. We don't know about the 0.7 and 0.4. That's what we want to predict. So this is 7 and 8. So we know now that the energy of this particle is 7 plus 8. It's 15 GeV. By the same token, we calculate the eta from the etas of the topo clusters, and we calculate the phi. From this, we can find the PT, and our proxy for the neutral particles, by which we will have the neural net to predict its properties, will be, in this case, the energy will be 15, eta will be this, and phi will be this. So using the predicted hypergraph and the given energies of the topo clusters, we can get a proxy for the neutral particles, which we, again, concatenate with the learned hyperedges, do an MLP to predict, in this case, the three quantities, delta PT 3 feature, delta eta, and delta phi, add to it the vectors, PT, eta, phi, and get the particle PT, eta, phi. So the overall hypergraph P flow algorithm will be the following. First, we predict the incidence matrix. We have a recursive learning with 16 refinement blocks, and we predict the hyperedges. We take this from them we can calculate our proxy quantities, both for neutral and for charge. So we predict our incidence matrix, from which we get the proxies. We take the hyperedge representation and concatenate it with the proxy, from which we predict the offsets, the delta, from which we calculate the properties PT, eta, and phi. This is a visualized way to show you how we get the proxy for this is of course a charged particle here, the one. But how we get the proxies for the neutral particles. It's what I showed you, but in a more general way. The boxes are the particles, the circles are the topo clusters, and using the learned weights here from the incidence matrix, we calculate our proxies using energy conservation. Again, start with encoding of the tracks and the cells, getting the tracks plus topo clusters. If you don't want to use topo clusters, you can skip this thing and do just embedding of the cells, not skip the last stage where you collect the tracks into when you collect the cells into topo clusters. the cells representations into topocluster representations. Then you do the learning of the hypergraph. Then you do the proxy computation. Then you do the correction, and you regress the particles kinematics and the class. So how well we are doing? Is there a question about all the machine learning stuff here? Because now I'm going to show you the performance. Let's stop for a second. I just want to make sure that you understand what was done here. So we had a detector output with tracks and cells. To make our life easier, we clustered some cells into something called topocluster, which is not a must, but we do it. Then we use machine learning hypergraphs in order to predict, using something like an attention, but it's not an attention mechanism, to predict using physics input, energy conservation, how much energy is distributed by the topoclusters into the various particles objects. We predict it. We use physics input to improve our regression, so we can regress less than just the whole PT, just some of it, because the incidence matrix already tells us the energies, gives us a good proxy for the energies. And then we, using the final representation, we also classify. And this is it. So how well we do it? Results. First, cardinality. How many truth particles are there versus how many we predict? This is a logarithmic scale. So you see it's very good, the performance, very good. We can also look for one event, for example, the incidence truth. Our K, the metric is up to 30. Okay? We allow up to 30 particles. So we can look at the incidence truth versus the incidence prediction, and this is just to give you the feeling that it's doing a very good job. Very good. Now you will see something you already met yesterday, which is called the Hungarian matching or Hungarian loss. We have our incidence matrix, we have our predicted matrix, but now we have to tell which particles belong to which particle. Which particle belong to which particle. Because we have a set and we get a set. So we do it with the Hungarian matching using delta PT, delta eta, and delta phi. And then to evaluate the performance, we do pools, which is take residuals. Take what we predict minus the truth and divide it by the truth to see the resolution. Okay, how well we do it. So, you have three methods here. Hypergraph p-flow, slot attention, which you're already familiar very well with, and the last one that really doesn't work so well, so I'm not going to talk about it. So I want to compare these two, the slot attention that we learned very detailed yesterday, and the hypergraph p-flow, which we learned very detailed today, and compare them. So you see that the hypergraph is really doing a great job in the neutral particle residual of PT. This is unbelievable that we even managed to do it. Same thing, I look for neutral particle, which is the real challenge here, for delta phi and delta eta. This is a very good performance. For neutral particle, there are no charge track here that helps me. And these are particles inside jets. I can also try to see what is the efficiency and how would I define efficiency. To do efficiency, I need also to know the truth, right? How good I'm doing, okay? So I have supervised links between particles and input nodes, and I can interpret efficiency. So match predicted divided by the target will give me the efficiency. So for photons, it's more than 90%, above 2 GeV. It's amazing. Fakes. How many are predicted as photon but are unmatched? And that's less than 5% for the hypergraph, and the rest are way above, you see? The TSP and the slot attention is here. The object condensation is not at all able to do it. Same thing here, the slot attention is a little bit below the hypergraph. Same thing for hadrons, not for photons. The efficiency is about 80% above 3 GeV, and it competes with the slot attention. Slot attention is a little bit better here. But when it comes to fakes, the hypergraph is doing much, much better than everything. Less than 10% above 20 GeV. Now, how will we classify the particles? So, what is the probability that the predicted neutral particles, which are matched to two photons, are really photons? How many particles that I match to photons are photons? More than 90% above 5 GeV. And this is this one, the photons. You see, the slot attention is doing a very good job as well. But when it comes to neutral hadrons, the hypergraph is really taking the lead easily. And now we try to look at global jet quantity. Remember the classical parameterized p-flow, which takes all the charged particles, predict how much energy they deposit in the calorimeter, subtract it, and by that avoid double counting, is tuned exactly to do a better measurement of the global jet energy, or PT. The particle flow, the classical is the shaded gray. The hypergraph is taking the lead by walking very easily. Much, much better, much better. Also than TSPN, easily. It's really good. Now we did something else. We never looked at gluons. We didn't train it on gluons. We said, okay, let's run the Monte Carlo with gluons and see how well we perform without training it at all. Without training, just to see if we can cope with that. And to our surprise, it did very, very well without being trained on gluons. That's the global energy reconstructed resolution of gluons when you train on light jets. Does it manage to predict the number of objects in a jet? In a jet. So how many constituents, how many particles? Here I count the number of particles inside a jet. To the distribution. And I see that I do very, very well. The truth is the shaded yellow, and the red is the hypergraph, and it's doing very, very well. And also here, very, very well. Now let's look a little bit in detail. Here's one event. You have the legend here. The legend is here. So first of all, the anti-KT jet is shown here for both the truth and the what comes from the hypergraph, and you can't even tell that there are two circles here. They really describe exactly the same jet. Second, the x's are the reconstructions, and the circles, the x's are the reconstructions, and the circles are the truth event. So, for example, for charge hadrons, it's doing a perfect job. The x's sit inside the circles. You see it here, inside the circles. For photons, it's doing a good job, but it doesn't manage to hit the target completely. For example, I have here 1, 2, 3, 4, 5, 6 photons, and the 6 photons are here. So there is it's still a little bit further away. Not much, by the way. Not much, by the way. This is eta phi. So not much, by the way. It's very close by because the scale is not all the way. It's a magnification of the scale here. But here you see that you see exactly how far it is when you look at the right scale. It's not exactly on point, but it's doing the job. Hopefully we will be able to do better. Another, here is I want to show you this magnified scale. So I show you that I don't really hide the problems. We are not on point, but we are doing well. First of all, we predict the correct number of photons, and we even predict the neutral hadron here, but we don't sit exactly in the same eta. Same thing, let's look at the chart, but the chart is perfect. It's no need to. Another event, a different event. Here I look at, you see it's doing a very good job here. In this event, it is a very good job. This X belongs to this neutral hadron. These are neutrals. And these are the charge hadrons doing perfect in the H-cal and in the E-cal as well, doing a perfect job. These are the photons and doing a perfect job. So some events doing better than others.
Can you say again what the x-axis on the left column is?
Yeah, I can. No. What's going on? Okay. The x's are the reconstructed photons.
I mean the x-axis on the left column.
Same thing.
Because it doesn't have a label.
It's the same legend. The same legend. Exactly the same legend. The neutral hadron are the black ones here. The blue ones are the photons. And the red ones are the charge hadrons.
And the x-axis also shows eta? Or
the x-axis is eta and this is phi.
Does this the size of this square on the rightmost plot represents the size of the calorimeter cell?
The boxes.
The boxes.
Yeah. So, first a comment before I summarize. I don't know how it works. I never designed the time, but it always ends at 1.55 if I have to give it in 1.5. If you gave me only 1 hour, I will finish in 1 hour. This is something that happens in the head of the lecturer, right? He builds this space so he can make it. This is amazing. No, I didn't finish yet. You have 4 minutes to go. Okay, so why hypergraph flow is superior, is so good, especially to slot attention. I already said it, the attention weights in the slot attentions are latent rather than physical meaning. HDP flow, it predicts the incidence matrix, which is a key in unrevealing the overlapping shower, but it also gives us a physical basis to energy contributions because it has a built-in physics inductive bias. So that's why it works so well, we believe. So my conclusions are two. First, hypergraph as proxies for particles enable physically interpretable results. They introduce inductive bias towards energy conservation, predicts interpretability from physics point of view, and shows excellence performance best in the study that we did. I need another 2 minutes. Hypergraph preference seems to provide solution to the long-standing particle flow problem, first time we see it, allowing to reconstruct particles inside jet, and in particular, it deals with neutral particles, which we didn't believe that one can do, which was amazing. So I covered the whole of the syllabus, and I finished my 3 lectures. So I thank you very, very much. And this is done with transformers. Thank you very, very much.
What's up with you? I think, by the way, this like natural, like sticking to time is something that you're all theorists, right? It doesn't actually happen in theoretical physics. I mean, I think this is something that experimentalists know how to do.
I mean, Lucas even finished before time yesterday, right?
Yeah, you probably need to type faster than he did. No, so thanks so much, Eilam. Are there more questions?
I have a question.
Here you go.
So you said that you performed well on the gluon jets, even though you hadn't trained on them. Did you expect that? Like, are they similar enough that you would expect the same performance?
I'll be honest with you, it's the referee who asked us, why don't you do it? And we were a bit scared, because if it won't work, we will have to sit down and think why it doesn't work. We did expect it, because if it's doing the right job, it doesn't care where it comes from. Besides, the theoreticians can tell you that light jets are not that different from gluons, right? Jets. I'm right, yeah? I mean, we should try it on bead jets. That would be more interesting, and we didn't yet.
But we know, yeah, I mean, quark with gluon jets, everybody who has ever tried to train them, right? It's just the number of constituents. That's nothing else. Or in other words, they have different color factors. It's CA versus CF. And that's the entire difference. So if you're not super sensitive to that number, there's no structure, we think. Which comes as a disadvantage if you want to tag them. So yeah, or more. Not that, then we need to thank Eilam again for 3 great lectures, for grounding us, like, making sure that we stay on the real axis. You'll be with us tonight, right? And you don't have to prepare a lecture, so you can actually talk to you.
Yeah.
Yes, okay.
If there's no rain, so.
If there's no rain. No, otherwise inside. So thank you, Eilam.
Thank you.
It's great to have you.